Hello everyone, welcome back to my channel. Today our topic is smart contracts vulnerabilities. There are 18 vulnerabilities DeFi exploits that I explain in this video. Before we start the all exploit, let's start with the one simple question. Why is smart contract security such a big topic in the blockchain ecosystem? Today, the smart contracts power almost everything in the decentralized finance. They run decentralized exchanges, lending protocols, stable coins, NFT marketplaces, DAOs, and even cross-chain bridges that connect with different blockchains together. And inside these smart contracts, billions of dollars are locked. But here's the critical difference between the smart contracts and the traditional software. Smart contracts are immutable. Once a smart contract, we all know, once a smart contract is deployed in the blockchain, uh, and its logic extremely difficult to change. Developers cannot simply push a quick patch the way they would in the Web2 system. If there is a Web2 system, then we change the database and some things, and like we fix it. The vulnerability exists in the code. It becomes permanent attack surface in the Web3, and attackers can study that code. Publicly analyze it and attempt to exploit it. Over the past decades, Web3 ecosystem has been major security incidents. One of the earliest and the most famous example was the DAO hack. The attack, that vulnerability is known the Reentrancy, allow the allow attacker to repeatedly withdraw funds from the decentralized investment contract, and that exploit drained millions of dollars and ultimately led to a major fork in the Ethereum network. Since then, the DeFi industry experienced many different types of attacks. Some vulnerabilities come from the coding mistake, other comes from the fluid economic assumptions, and some come from the complex interactions between the different protocol. So in this video, we are going to break down the 18 major smart contracts vulnerabilities that every Web3 developer should understand that. So the smart contract security matters. Like why this matter? Because they have a critical application. Also include like decentralized exchange, lending protocols, stable coins, marketplaces, and that how that works. Smart contracts and here the DeFi protocols, like financial apps, and billions of dollars locked inside this. And real exploit that we talk about, the DAO hack, the cautionary tale. Infamous DAO hack in 2016. In that earliest and the most impactful exploit in the Ethereum network, highlighting the critical importance of the smart contract security. In that, what they do in the Ethereum network, the foundation of the decentralized application, and the another contract is the DAO smart contract, and manage that large decentralized fund in that DAO smart contract. They launch a reentrancy exploit, the malicious recursive call, drain funds, like they call again and again. Reentrancy matlab they are written in that contract again and again and drain funds, and they're like funds drained like $60 million ETH stolen, led to the hard fork. And then like Ethereum hard fork happened. The incident result approximately 60 million US dollars worth of ETH being drained, and leading no conversational hard fork the Ethereum blockchain to recover the stolen funds. That stolen fund not recover till now also. So it served as a stark reminder of the irreversible nature of the smart contract vulnerabilities. And then in this video, we are going to break down the 18 major smart contracts vulnerabilities that every Web3 developer should know and understand. And we look at that and like how each vulnerability works, how attacker exploit it, real hacks, where it happens, and how developers protect their systems against this risk. There is a 18 major smart contracts. So first is the reentrancy attacks, integer overflow and integer underflow, access control bugs, MVV, and the front running flash loan attacks, oracle manipulation, delegate call vulnerabilities, unutilized contracts, denial of service attacks, timestamp manipulations, weak randomness, logic design and errors, cross-chain breach vulnerabilities, storage collision, signature replay attack, self-destruct risk, gas griefing, upgradability risk, and there is many other also, but like we cover this 18 major. So the sum of the vulnerability caused some of like biggest hacks in the crypto history, including the breach exploit, worth hundreds of millions dollars in the DeFi attacks involving the flash loans and oracle manipulations. By the end of this video, you will understand the how most important the security risk in the smart contract development and how modern protocols try to defend against them. Before we dive into that vulnerabilities themselves, we first need to understand something important. Why the smart contract security is critical in the first place. We need to understand why smart contract security is such a big challenge. Because the way blockchain system work is fundamentally different from the traditional software ecosystem. In the normal web 2 system, web 2 application, there is a bug is discovered and the developers can simply deploy an update. They patch the backend, update the server code, and the issue is fixed. But in the smart contract, they don't work like that way. Once a smart contract is deployed to the blockchain, it codes becomes a part of the network's permanent state. Every node is in the network is running that same code. So if the vulnerabilities exist in the deployed smart contract, then it's not just a bug, it become a publicly visible weakness that anyone in the world can analyze and try to exploit, and becomes even more dangerous in the world of decentralized finance because that are related like a stocks. So, because these smart contracts are not just running on the small application, they are controlling massive pool of money. Some DeFi protocols manage hundred of millions, sometimes billions and billions of dollars in assets. Like all of that value is secured purely by the code. There is there are no banks, there are no centralized administrator. So the smart contract itself become a financial infrastructures. So now imagine what happens when the attackers discover the weakness in the infrastructures. They don't need to hack a server. They don't need a into database. They simply interact with a protocol exactly the way it is programmed to behave. And that's one of the most important ideas in DeFi security. Many attackers are not about breaking the rules. They are about using the protocol's own rules against itself. So another important factor in the DeFi protocol are highly composable. Different protocols interact with each other constantly. A lending platform might depend on the price data from a decentralized exchange. That exchange might depend on a liquidity pools. Those liquidity pools might depend on a token from other protocol. Like you understand, or like it's crazy, so we understand better way. A lending might depend on the price data on the decentralized exchange. That exchange might be dependent on another liquidity pool, and that liquidity pool depend on the tokens and then some protocols. So it's like interconnected structures created, so that extremely powerful financial system. But we have to collectively, and we have to like all the components and all the protocols like interconnected, that it's properly and without a bug free, that we have to understand that if the component behaves unexpectedly, the impact can spread across the multiple protocols. Like this is the smart contract controls the financial value in the decentralized exchange facilitate token swap like Uniswap. They are in the decentralized exchange. We call that a DEX also. Then lending protocols like Aave, Compounds, they are enabling borrowing and lending things. Stable coins like maintaining the pegged value of, they are stabling the coins like USDC, USDT. Liquidity pools like providing capital for trading. NFT marketplace governing the digital assets of transactions, cross-chain bridges that connecting different blockchain network. Many DeFi collectively manage hundred of million of billions of dollars like that way. Here's the smart contract that code automate financial rules, and the DeFi protocols, the composable system built on the contract. They are connected with the contract and the liquidity pools that enables trading and lending, and billions of dollars locked in the massive that secure on-chain value. And the how we, like DeFi attack work. actually work. In decentralized finance, attackers typically do not hack server or database. They would traditional as they would in the traditional system. Instead, they interact with the smart contract exactly as program. Like in Web 2, they have to hack the database or their server to like hack or like uh, attack on that company or attack on the particular system. But in the decentralized, they don't want to hack. They have to interact with the smart contract, and what they have, like they hack the server and they are interact with the smart contracts on what are the program they understood with they are publicly available. Many exploits economic attackers where malicious actors manipulate protocol logic and market condition to their advantages. Like they are interacting with protocol, they are like manipulate market condition, they interact with the protocol so they can manipulate the market condition also, and they do the exploit protocol logic and that extract the profit out of them, and then the DeFi attack happen. Another major factor that changed the DeFi securities landscape is something called flash loan. And flash loan allow someone to borrow a massive amount of capital for a single transaction, as long as the loan is repaid before the transaction finish. That means attacker no longer need to have a larger amount of money to perform an attack. They can temporarily control tens and even hundreds of millions dollars, manipulate the market conditions and exploit the vulnerabilities, repay the loan and keep the profit. Like we can do with the bank system. What bank do? We can go for we can get a loan from a bank. That loan we put in some business or some shares, and if we like income from the shares and we are repay that bank loan and we get some profit on that. That's the same way flash loan do this in the decentralized world, in the DeFi world. They allow to borrow the amount of capital for the like do the transaction in decentralized world. Then they go for the price oracle. If sometimes that happen, there are the different price oracle, and there is a it's very little difference on the like. So what the attacker do also, they borrow the loan from the lending protocols like flash loan. They do the flash loan. So they go to the one price oracle and buy from that like a Dogecoin that is like 2.5. So here's the price. The one Oracle price have a Dogecoin 2.5, and the other is a 2.6. So there is very little difference between them. So like they buy from the Dogecoin from the 2.5 and they sell all the Dogecoin in the other Oracle at a 2.6. After that, to sell in the 2.6, they pay all the loan to the lending protocols, and whatever profit they get on their account, and like DEX liquidity pool, like price oracle from the DEX liquidity pool, and the external tokens, they get a token like that way. That means the attacker no longer needed to have a large amount of money to perform an attack. They can temporarily control tens and even hundred and billions of dollars, manipulate the conditions of the market, and exploit vulnerabilities, and then repay the loan and keep the profit, all within a single transaction. Because of this, many modern DeFi exploits combine multiple techniques at once. An attacker might take a flash loan, manipulate a token price, trigger protocol liquidation mechanism, and extract value before the transaction completes. And that's why smart contract security is such a critical field today. Developers building DeFi system are just not writing the code. They are designing the financial infrastructure that operates fully adversarial environment. Every functions, every state change, and every external interactions must be designed with the assumptions that someone will try to break it. So here the flash loan attacks, there is a define more here, like flash loan borrow, that price manipulation, and the protocol exploits and repay the profit. So Now we understand the security challenges of the smart contract. Let's move to the first contract or first famous vulnerabilities in Ethereum history is like reentrancy attacks. Reentrancy happens when the smart contract sends funds to the external address before updating its internal state. There is a it's a minimal definition of that. It might sound like a small design mistake, but it's in the blockchain environment it can be lead to like bigger mistake. To understand how it's work, let's walk through the simple example. Like imagine you have a smart contract that allow to deposit ETH and later withdraw their balances. A simplified withdraw functions might look like this way. So here they are mapping address to UNTF public balances and function. This is the function of withdraw and the public that also public and require balances message.sender and it's greater than equal to the amount. External call made before the state update. This is the external call. There is a bool success message.sender call value and amount and require success message and state update occur too late. This is a state update call uh, that shows to the owner after the this call is happened withdraw they show the balances. Like what happened at a first glance you see it's look like a correct, yeah, if after the external call and before the state update and the state update occurs too late. So here's you say see that state update too late, but like at a first glance it look like a correct. Contract checks that user has enough balance, like here we check the user have enough balance, then send it to the user and finally updates the state. But it's subtle problem here. The contract sends ETH before updating the balance. The contract already sent the ETH before updating the balance. Here we say also before state update. Like the fallback function can withdraw the function again before the balance was reduced. So execution flow look like user call the withdraw transaction. User call this withdraw and contracts send the ETH. Then receive fallback execute like they receive fallback execute and fallback withdraw again and again, like now they fall back again, they the same transaction they again and again. This is the exploit contract. If that mistake in the contract will exploit like that. So fallback calls withdraw again and balance still unchanged, like whatever the like user they are waiting for the balance update. So funds withdraw again and again and balance still unchanged, and after like they see after the whole contract finished all balance and then contract update with the zero balance. So this process can repeat multiple times. So instead of withdrawing their balance once, the attacker can withdraw the it money inside. Attacker can withdraw it many times in the same transactions. Is a one transaction happen and like attacker can withdraw many times from here. This is called we call re-entrancy attack. Re-entrancy, re-enter, like again and again enter. Then the other attack is the DAO hack. One of the most famous example of the vulnerability was the DAO hack. The DAO was the early decentralized investment fund built on the Ethereum. The people could deposit ETH into the DAO for and vote to investment proposals. Like at its peak, the DAO held about $150 million of worth of ETH, and which was numerous amount of at any time. So, however, the DAO contract contains the re-entrancy vulnerability in the withdrawal logic. An attacker exploits this flow by repeatedly calling the withdrawal function through the fallback function. As a result, the attacker managed to drain the 60 million worth of dollar in this DAO. The DAO communities like in this incident was so significant that led to one of the most controversial event in the blockchain history. The Ethereum community decided to perform the hard fork to the network, then reverse the hack and recover the stolen funds. Like then hard fork eventually created two separated blockchain, and they do hard fork like in Ethereum, and that separated into two separated blockchain like Ethereum and Ethereum Classic. Ethereum is like ETH and Ethereum Classic defined as ETC. How the developer prevent reentrancy. Then we know that how the developer prevents reentrancy. There is a several best practices to developer follow for the reentrancy attack, prevent the reentrancy attack, like checks effect interaction pattern. In that, the safest approach is update the contract state before making external calls. So instead of sending ETH first, we update the balance first. Secure function is look like this. First we do the withdraw function, then required balance of message, and then balance message. What are the effect, like what are the balances divide from cut from the balance that amount, and after the message of the success interaction message. So now even if fallback function tries to call a withdraw function again, then the balance is already reduced. So now even the fallback function tries to call a withdraw again, the balance has already been reduced. Second is reentrancy guard. In that, modern smart contracts library provide the built-in protections also. For example, there is an Open Zeppelin provides a contract called Reentrancy Guard. That is an Open Zeppelin library, and that we can use with the reentrancy contract, like reentrancy guide with the import of Open Zeppelin library, and then function call of withdraw and external non-reentrant, so that also we prevent from the reentrancy attack. So non-reentrant modifier ensure that a function cannot be re-enter again while it's already executing. If that function is one time execute, then the balance and the function will be closed. Not before that time, that function is continuously. So this is the process of like how we prevent from the reentrancy attacks. Another is the pull payment pattern for the reentrancy preventions. Another secure approach is pull payment model. Instead of automatically sending funds to the user, the contract records the amount earned and lets user withdraw it themselves. Like they reduce the risk of the external call vulnerability. Reentrancy attacks taught the blockchain community a very important lesson. Every small ordering mistake in the smart contract logic can lead to financial losses. And this vulnerability is exactly why the security pattern like check affect interactions become a standard practice in the Solidity development. So there are the three prevents how we can prevent the reentrancy. So now the next vulnerability we look at a second, like integer overflow and underflow. This issue exists early version of Solidity because of many smart contract bugs. To understand this vulnerability, we need to briefly look how number are stored in the smart contract. And Solidity uses fixed size integer types such as uint8, uint16, uint32, uint256, like this kind of fixed size integers. Each type has a maximum value it can store. For example, uint8 variable can store only the numbers from the 0 to 255. Now what happens if we try to add 1 to maximum value? Like uint8 is equal to 255, x is equal to x plus 1, then expected is 256, but uint8 only stores 0 to 255, so its actually numbers happen is 0. Because the variable cannot store number larger than 255, the value wraps around back to 0, so the result becomes the 0. This is called integer overflow. And similarly, we have integer underflow. So here we have an example like uint8 x is equal to 0 and x is equal to x minus 1. So what you think? You expected minus 1, but again uint8 is only store the 0 to 255. Since the unsigned integers cannot be negative number also, the value wraps around the maximum value. So that the result become a 255. So why this was dangerous? Because before Solidity version 0.8, these arithmetic operations did not automatically throws error. So if developers forgot to add safety checks, attackers could manipulate balances. For example, like imagine a token contract that subtracts balances without checking underflow. So an attacker could cause the balance calculation wrap around and end up with a huge token balances. To prevent this, developer used a safety library called SafeMath. provided by the Open Zeppelin. For that, like example of that, mm, like here. There are safety library by Open Zeppelin. Starting from Solidity version 0.8, overflow and underflow checks are built into the language. If an arithmetic operations exist that allowed range, the transaction automatically reverts. However, the developer can still disable these checks using the unchecked keyword and unchecked keyword for the gears optimization, like they unchecked and counter plus plus, then the developer can still the careful when using unchecked arithmetic. These arithmetic vulnerabilities may seem simple today, but in the early days of Ethereum they were a major source of smart contract bugs, and they help shape many of the security practices used in the modern security developments. Here's the how we can use the safe met protection solution of the overflow vulnerabilities. So how that opens a plane using this, and vulnerability token using SafeMate for the UN 256. So they already use that. So any developer calls, yeah, any user call beyond the like UN 56 amount, then they goes to the revert the transactions not submitting or not like even another. So here's a SafeMate sub function checks to underflow. Balance is message.sender is equal to balance message.sender point sub amount. It's a sends token. SafeMate ensure that overflow and underflow operation automatically throw an error. If that overflow or the underflow both are handled by the SafeMate library, and transactions revert automatically if an unsafe arithmetic operation is directed to prevent state corruptions. And here we already talking about like after this vulnerabilities, Solidity 0.8.0 above that. After 0.8.0, they are already built-in checks overflow underflow happen with the arithmetic things. So modern contract like look like that way. They don't need to use if they don't use OpenZeppelin SafeMate, then also that will be fine. So modern contract public counter type u into 56 dot max value for the u into 256. Increment counter public counter plus 1. This will automatically revert due to overflow, and same kind of like no overflow check, that is a increment unchecked. So public unchecked counter plus plus no overflow check will wrap around if counter is max u into 56. However, that behaviors, the transaction automatically reverse, preventing unexpected wraparound behavior. But however, the developer exploitly disable this checks using that unchecked thing. If they do the unchecked block for the specific operation, this is typically done for the gas optimization in the situation where the developer is absolutely certain that overflow underflow cannot occur when they intentionally want the wrap around behavior like this function. Then the third one is the next category of smart contract vulnerability is the access control vulnerabilities. In many cases, these are not complex technical bugs. They are the simple design mistake where the sensitive functions are not properly restricted. In smart contracts, certain operations should only be performed by privileged account. For example, minting a new tokens, updating price oracles, upgrading contracts, implementations, posing protocols, operations, um, managing treasury funds. If these functions are not protected correctly, anyone can call them. Let's look a very simple example. Like imagine a token contract that includes a mint function inside this. Like we can find here, simple mint function. So address user and u into 56 amount that are public, and balance user plus n is equal to amount. So at a first glance, this might look be harmless. You think that is a harmless, this is the okay good contract, but there is a critical problem. The function is public here. There is no restrictions who can call it. That means anyone can mint tokens. An attacker could simplify call the function and create unlimited tokens for themselves for with their address. So this would immediately destroy the token economic value. Like how attackers like visualizations. Attackers they call the mint function, they create unlimited tokens and protocol economy is destroyed because we have to any tokens they have to proper stabilized token. So the access control makes mistake is have a caused many problem in DeFi ecosystem. Sometimes developer accidentally expose administrative functions as are like such a set oracles, upgrade implementations, and post protocol that also be if an attacker gains access of these functions, they may be able to manipulate the whole protocol. For example, imagine a lending platform where oracle access can be changed. If an attacker sets the malicious oracle, they could feed fake price data into the system, and that fake price could allow them to borrow huge amount of assets using worthless of collateral. Like this is a huge risk. So the how developers secure this access control. So to prevent this problem, smart contracts typically implement the strict permission systems. The first is like ownership pattern, role based access control, multi signature governance, and time lock contracts. So first we see the simplest approach of the ownership pattern. So here the address of public owner modifier is only owners require message.senders is equal to owner or a not owner. Only owner can require this access. And function mint address user and u into 56 amount public only owner. Before that we only do the public, but here we mention that public but only owner can do this. Mint balance is user plus amount. The sensitive function use the this is the sensitive functions use the modifier. Now only owner can mint the token of that. The second is role based permissions. For most complex system, developer use a role-based access control. Instead of a single owner, different roles are defined. Like a example, they have a admin role, poser role. Like now the token is like mint, and after this thing, after that, that much token already mint. After they pose, like so, the another have a poser role, upgrader role, each role can perform specific actions. Security library from OpenZeppelins provides widely used implementation for the role management and role-based access controls also. A multi-signature government governance is the large DeFi protocols. A single in the large DeFi protocols, a single private key controlling admin function is extremely risky. If their key is compromised, the entire protocol could be taken over. So, to prevent this, many protocols use multi-signature wallet, such as Gnosis Safe. Gnosis Safe means safe wallet. You understand about they have a multi-sign thing. So there were multi-sig wallets, multiple team members must approve the transaction before it executes. So if the like any one wallet is also exploits or like hack, so they can't exploit the whole team members wallet. The everything like happen the one wallet, not whole team wallet. So they do the gnosis safe. So the multiple team members can access that if they all sign that approval, then that's transactions or like something whatever they want to execute that happen. So and the other is the time lock contracts. The another important protections mechanism is the time lock contract. Time lock delay the sensitive operations such as upgrade. For example, like upgrade schedule wait for the 48 hours, so an upgrade executes. First upgrade proposed, then 48-hour delay and upgrade execute. This gives the this delay gives the community time to review the change and react if something malicious is proposed. So that if anything upgrade is proposed, then that schedule after some time. So in that time, the all the developer and other peoples are see that contract properly, and if that is anything, so before the execute, we can change the malicious thing inside that. So access control vulnerabilities may seem simple, but they are extremely dangerous. The single exposed admin functions can be a taker full control over an entire protocol. That's why permission management is one of the most important aspects in the secure smart contract design. Our next topic is MEV front-running attacks, which are extremely common in decentralized exchange. To understand these vulnerabilities, we first need to talk about something called mempool. When you submit a transaction on a blockchain, it is not immediately include a block. Instead of first enters a public waiting area like called a mempool. So this is the where pending transaction sits before validators include them in the block. So the important thing to understand is that the mempool is a public. Anyone can see the transaction waiting to be executed, and this creates an opportunity for attackers. They can watch the mempool, detect that profitable transactions, and submit their own transaction with the higher gas fees so that transactions are executed first. This behavior known as a front running. It is the part of broader concept of maximal extractable value. So that is MEV. So how that here user transactions happen and here's the public mempool, and MEV bot detects that mempool and they see that transactions what are the best for them, and the bot send the higher guess. So what are the validators do? Whichever transactions have a higher guess, they prefer that first, so that bot executes the first. So in here, the one is sandwich attack. So the common one of the common MEV strategies in the sandwich attack. Let's look how that work sandwich attack. Imagine user is about to perform a large swap on the decentralized exchange. For example, swap 100 ETH for USDC. So that is 100 ETH means the larger swap. That transaction enter the mempool. MEV bot detects that enter the mempool, and the MEV bot detect the transaction, realize that it will move the marketplace because someone transact like 100 ETH to USDC, so the market price something difference, the move that market price. So the attacker sends two transactions. The sequence look like the attackers buy token first, victim executes swap. Victim means the person that transactions of 100 each swap, that is a victim. So attackers buy the token and the victim executes swaps and attacker sells the token. That it creates a sandwich like around victim. Victim means the here's the victim and the two side of attacker. They buy and sells both together. This creates the sandwich around the victim transactions. The attackers buy the first, which pushes the price up because he buys the first, and the victim swap execute the worst price at a worse price because the and finally the attacker sells the higher price, capture the profit. The victim ends up paying more for the trade due to slippage of transactions, so they have to pay the more amount. So platform attacks like this platform sandwich attack extremely common on the decentralized platforms like DEX platform, such as we have like knowing about DX platform like Uniswap, SushiSwap. That's a swap platforms like. Automated bots constantly scan the mempool and looking for the profitable opportunities. And some of these bots execute thousand of transactions per day because they are doing by the bots, not a public. No, they personally see and do the transactions and that. So how developer use the migrate MVV? Here we also mention like MEV bot buys token, that is red. In red they buy token. Victim swap executes blue and green. Like we mentioned the color. And where at the platform that kind of attack with that. So how developers user mitigate MEV? While MEV cannot be completely eliminated, several mechanisms reduce its impact, like slippage limits. So we understand first about the slippage limit. DEX interfaces allows user to define maximum slippage. So example like swap 100 ETH, minimum amount is 195,000 USDC. So the If the price is changes too much during the transaction, the trade automatically fails. Like you user set a maximum acceptable price change for that trades on DEX. If the market price moves beyond this tolerance due to MEV bot or volatility, transactions automatically reverse because that high price they cannot get, and protecting user from the unfavorable executions. Like user trade, then price move the down and transaction reverse because the price move down. This prevents attacks from the profiting at the user's expense. Then the another is the private transactions release. Another approach is using private transactions network. Instead of broadcasting the transactions to the public mempool, user can public mempool. It can send directly to the block builders, and the system like a flashbot provide this functionality. System or like server like flashbot that enable this and preventing MVV bots from seeing and exploit pending transactions. Like here the user wallet, then private relays and block builders and block execution. This eliminates the visibility advantages of MVV bots rely on. These are the protections. That MVV protection tool. Server wallets and services now offer MVV protections by default. So these tools route transactions through private relay to avoid front-running bots. Then MEV and the front-running attacks highlights a very important reality of blockchain system. Because the transactions are the transparent before executions, the attacker can use that information and extract that value. Understanding how the mempool works is essential for the designing secure and the fair DeFi system. Like many protocols, wallet and DeFi platform integrate automatic MVV protection. So that how that use this tool intelligently route transactions through private channels and use specialized algorithm to obfuscate transactions intent, safeguarding user from the various MVV attacks. Like MVV aware wallet, then they go for the slippage limits and the secure executions and private RPC they're going for. Example include flashbots protect and the certain MVV awaits RPC. Then the against come the next vulnerabilities categories we need to understand is about the flash loan attacks. We understand before that little bit about. So flash loan are one of the most innovative ideas to introduce a decentralized finance, but they also completely change the security landscape of DeFi. To understand why flash loans are powerful, we need to first understand how borrowing normally works. In traditional finance, if someone wants to borrow money, they usually need to collateral. For example, if you borrow the $1 lakh, the lender wants to know you repay it. But in flash loan works differently. Flash loan allows someone to borrow a large amount of assets without collateral as long as borrowed funds are returned within the same transactions. Like if the loan is not repaid by the end of the transactions, the entire transaction automatically reverts. Like for the only one transaction, they get a flash loan, and after the complete that transaction, the loan get revert. And if they not give that flash loan amount, then their transaction also revert. So the from protocol perspective, the loan either gets fully repaid instantly or it never happened. Flash loan were popularized by the DeFi lending protocol like Aave. They were originally designed the legitimate use case of such arbitrage, refinancing loan, and liquidations. But attacker quickly realized that the flash loans could be used for the temporary control massive amount of capitals. Even if an attacker has no funds, they can borrow millions of dollars from the for a single transactions, and that make a certain attack much easier to execute. Basic how the work like basic flash loan structures. Let's look like simplified loan structures. Borrow funds and then execute that operations and the repay loan. Like simple structures that happen like that way. Everything happened, but everything happened in a one transaction. If repayment step fails, the transaction is reverted and the blockchain state remain unchanged. So the typical flash loan attack flow is like in many DeFi exploits, attacker use flash loan to manipulate protocol conditions. Like the typical attack might look like borrow the large flash loan, manipulate the price in the low liquidity pool, then interact the vulnerability protocol, and they extract from that profit and the repay flash loan. Like this way, the flash loan attack is happen. Because the attacker temporarily controls a large amount of capital, they can create a artificial price movement also, or a trigger protocol logic what normally be impossible, because you can flash loan the bigger amount and you do the transaction. Thus like example of code, how developer execute the flash loan operations. There is execute flash loan. So here the borrow funds, here what does happen, borrow funds from the lending protocol like Aave. The flash loan function will call back to the contracts and receive flash loan function to execute operation. There is a lending pool flash loan, and this token and amount by this bytes. After this line, the loan must have been repaid, handled within the received callback function. Receive flash as a sender, token amount, and fill. Perform operation using the borrowed funds and exploit arbitrage opportunity, liquidate position, etc. Like they have put a manipulate market and exploit protocol also, and the repay flash loan plus fee, whatever the fee for the borrowed like borrowed amount plus fee. So the lending pool will pull the funds back. So how the entire sequence this entire sequence must completed successfully inside the one transactions, and the how real world flash loan the flash loan have been involved in many major DeFi attacks like BZX flash loan exploit in 2020. That BZX flash loan exploit was one of the major flash loan attacks. Attackers borrowed the funds using a flash loan, manipulate the price on a decentralized exchanges, and exploit the protocol logic. The attack resulted approximately 18 million of losses. The second is like a harvest finance exploit. Another major incident was the harvest. This in this attack, the attacker used flash loan to manipulate the price of stable coins inside the liquidity pools, and by repeatedly depositing withdrawing funds during the manipulating price condition, the attacker drained roughly 34 million from the protocol. That's 8 million lost first, and with the price stablecoin price, they do the 34 million. So why flash loan made attack easier? Before flash loan exists, attacker needed to large amount of capital to manipulate the DeFi protocol, because they need if they move to market in the larger section, they have a large price and big price amount. But if that flash loans remove that limitations for them, now anyone can temporarily control tens and even hundreds or like even millions of dollars in liquidity. It means attacker can manipulate the market price, exploit protocol logic, and like trigger liquidations, drain liquidity pools, all within a single transactions, because flash loan we have to pay in the single transactions. Flash loan essentially democratized attack capital, which made a DeFi protocol much more vulnerable to economic exploits. Because of this, modern protocols design must always assume that attacker can access unlimited liquidity. Before flash loans, they have to execute significant manipulations or exploit. Attackers typically needed to possess and acquire a substantial capital, the limited scope and frequency, and attacker well-funded entities, but needed a large capital and the control markets, limited access of the large funds, fewer slower attacks opportunities. But after flash loan, they have a manipulate market prices on DEX, exploit protocol logic flows, trigger cascading liquidations, drain liquidity pools rapidly, All this operation could be executed within a single atomic blockchain transactions, leaving no time of intervention. And here the resource intensive and requiring attackers to accumulate the necessary assets in over a time. And here the income, like, they earn more amount because of they have more money. Next vulnerability we need to understand is the oracle manipulations. For example, lending platforms need accurate price to calculate in a collateral value, liquidation thresholds, and the borrowing limits. These prices are provided by the system called oracles. If an attacker can manipulate the price and exploit the protocol economic logic. Example like oracle vulnerabilities. Some early DeFi protocols use a price data directly from the decentralized exchanges. For example, a simple price calculations might look like a price is equal to reserve A divided by reserve B. This formula reads the price directly from the liquidity pool. The problem is that liquidity pools with a low liquidity can be manipulated. If the attacker performs a large trade in that pool, the price changes instantly. If a protocol reads the manipulated price, it may take an incorrect decision. Typical Oracle manipulation attack. Let's walk through the Oracle manipulation exploit. Attacker takes a flash loan. Take a flash loan. Attacker manipulates the token price in DEX manipulation, like they have a DEX manipulation, and protocol reads that manipulated prices. That protocol reads that prices of manipulations and collateral value become inflated. Attackers borrow the large amount of assets. Attacker repay the flash loan, and attacker keeps the borrowed funds. That is the what they do in the Oracle manipulation. Because of the protocol trusted the manipulated price, it allowed the attacker to borrow more funds than they should have. So, what is the one kind of attack that happened in this like Oracle? One of the most famous Oracle manipulations attack was the Mango market exploits. In this attack, like in October 2022, in this attack, the attacker manipulated the price of the Mango token on the decentralized exchange. By artificially inflating the token price, the attacker made their collateral appear extremely valuable. Using this inflated collateral value, they borrowed extremely like 114 million worth of assets from the protocol. This incident demonstrated how dangerous price oracle manipulations can be. So, how we can prevent the oracle manipulations? To reduce that risk, modern DeFi protocol use more secure oracle manipulations, oracle mechanism. Time weighted average price TWAP. Instead of reading at a price of a single moment, the price calculated average price over time. So average price over the last 30 minutes, or it make a short term price manipulations much harder. Like they have manipulation for the 2 3 minute in 1 minute or like some seconds. Then this average price of 30 minute is harder. Then the other is a decentralized oracle networks. Many protocol use specialized oracle networks such as a Chainlink and Python network. Uh, this system aggregate price data from a multiple sources and validators, making manipulations significantly more difficult. Oracle manipulation attacks highlight an important reality of DeFi. Smart contracts are only as reliable as the data they receive from the outside world. If the data can be manipulated, even perfectly written smart contract code can still exploit. Here, the like, if I make it the whole vulnerabilities together, then it's like a too much big video happen. So we are doing the part one and part two. So in this part, we understand till six vulnerabilities we understand here, and other all vulnerabilities we understand in the part two. So here's the part one. So goodbye everyone. We meet in the next part.